Thank you very much. Good afternoon, ladies. So today, inshallah, we continue our course. So basically, in chapter 5, we finished modeling the MOSFET, or part of MOSFET. We studied 3 regions of the MOSFET. What are the 3 regions of MOSFET? MOSFET works in 3 regions. Region 1, region 1, 2, region 3. منطقة 1, منطقة 2, منطقة 3. What are the 3 regions? Saturation, I heard that. Huh? What else? Huh? Huh? Repeat. Triode. Huh? What's the 3rd region? Overdrive voltage is a region. Of course not. So, cutoff. Yes. Cutoff, triode, saturation. Very good. We know the conditions. I'm not going to ask you because I'm sure you did not revise. Makes sense. صح, makes sense? 100%. So this is a recording, a proof. They did not follow my recommendation. They did not revise. ولكن wait. What I said after each class you revise. صح ولا لا? You're not following the step. خلاص. It's your responsibility then. Huh? صح ولا لا? Make sense? Okay, let's move on. So we modeled that transistor in 3 regions and etc. We presented the equations for each region, huh? And we have the condition for each region. We are not going to repeat that. It's your job. Makes sense?
Yes.
But we finished last time with the saturation mode. We said that if, what's the condition for saturation?
VD equal or greater than VOC.
The overdrive, yeah. If VDS is above the overdrive, we are in saturation, huh? And of course we have to have the channel, and the channel condition is?
VGS equal VT or
greater.
Greater.
Yeah.
Equal or greater?
You said equal. It has to be greater. Okay. No, there is no equal. Just 1 point. Huh? Okay, so it has to be greater than VT. Very good. So we have to have these 2 conditions to be in saturation. Now, in saturation, what did we say last time? We said this, if you remember. Of course, we have solved this. We have this model, yes or no? In this model, we said that we have input, which is VGS, and we have the output, which is ID. So, and that's the definition of transistor. Huh? From first class of this chapter, we said that the voltage of between 2 terminals, drain, gate and source, controls the current on the 3rd terminal, which is the drain. That's the definition. Remember, huh? That's the rule. And we said that this voltage controls this current through this formula, creating what we call a voltage-controlled current source. That current goes there. That's it. And this is where? This is in the saturation. So this model only works in saturation region. Make no mistake. Very good. Why? Because we do amplification in saturation, not in triode. Okay, why? Because in saturation, our transistor works like a voltage-controlled current source. And amplification need current sources. Very good. And we said, oh, the resistor gone. We said that the resistance between drain and source is so high. Why? Because the voltage between the drain and source does not control the current. The current is controlled only by the current source. The current source who created this current is controlled only by VGS, which is this voltage. So no matter how much we increase VDS, the current will not change because of VDS. Okay, it changed only because of this guy. So that's why we said that delta VDS over delta IDS or delta ID is going to be infinity, which is the resistance. Yes or no? Which is that big resistance. It's so high that we can basically throw it away. Okay? And we know that I just explained why it's so high. Good. So this is the model. Today, actually, we are going to add a little change. And we say that, well, in reality, actually, VDS control a bit the drain current. How? We will see that. Okay? So what we said before is ideal. It's not real. But in reality, there is. And that's basically what creates what we call the output resistance. So that resistance that we said we throw it away is an output resistance. Why? It's output resistance because it is at the output, remember? This is the output, this is the input. I input voltage, I get current. That's it. No? You understand? So that resistance that is at the output was actually infinity. Now today we will learn that's not infinity. It is big, yes, but it has value. Alright, good. So let's keep going. See, that's why revision is important, because without that, without this little refresh, you will not understand the next. And if you build something over something bad, the whole story will become bad. That's why you need to revise. Okay? Do you understand? That's the point. So you have to keep revising. Okay, good. So that's what we said here, just we are going to explain it later on. Okay, alright. So the question is, what is the effect of increasing VDS on the N-channel current, okay, once the pinch-off has occurred? We'll explain that in a second. And I'm not going to go through here these answers. You will see these answers explained in here. So this is basically our transistor. Let me draw it for you. So this is the source. Okay, come here. And this is the drain. Come here. And here we have the gate. Voila. And then there's the gate, which is this terminal. Of course, it's an insulator here. This is the N+. This is N+. Here I put this in blue is the physical structure, is the material itself, okay? And here what you see under is the electrical things. So what we said that last time, but now we repeat again. We said that the channel here, when VDS becomes big, VDS means the voltage from the drain to the source, VD minus VS, when it increases more and more, it will change the voltage across the channel. So meaning that here right at the source, near the source here, the voltage of this column, for example, here, is actually V over drive. The voltage of the channel here is V over drive. But the voltage here, near the drain, actually, before we reach the pinch off, we'll get back to that. So which color we choose? The green. So here, oh, not this one, this one. So here is when the channel initially, when we start the pinch off, we'll explain the pinch off. Here, right at the drain here, of course here, I have to make some identification. The gate goes all the way to the drain. So this is the whole is, okay, now green. Okay, good. So here at the end of the drain is actually the voltage. It's not only voltage, it's V over drive here. Oh, that's me write it in red. So here, and then in the channel here, in the column of the channel here, the channel voltage is actually V over drive minus VDS. So as soon as VDS equals V over drive, this is the effective voltage across here, which is VGD. As soon as VDS equals V over drive minus VDS, which is the channel voltage at this point, becomes what? Becomes 0. And we said that in order to have a channel, the channel charge here need to have a voltage above, or the overdrive, above, or the effective voltage here has to be above 0, okay? Or VJD has to be above VT. And you can go back and see that. So now, if the voltage of the channel here is 0, the voltage times the capacitance to get the charge is going to be 0. So there will be no charge here at the drain part here. Okay? Because there's no voltage there. Effective voltage for the channel. Excellent. So, the charge will start disappearing from here as soon as VDS reach the overdrive. Excellent. At that time, at that moment, we say that we have what we call the pinch-off. And we explained that last time as well. Okay? Pinch-off. Pinch-off is basically if you take a tube of water, for example, and you squeeze it with your hand here and there, and becomes like this, for example. Like that. So the water is coming like this, for example. So here you are pinching off that thing. So that's it. So the channel stops here. There will be no more channel. As we do increase the drain voltage or VDS voltage, this voltage now becomes negative. So not only we don't have a charge, we don't have a charge at all there, and the pinch-off actually it starts to move on the other direction, which is here. So the channel become looking like what? It become looking like this. So this, so now pinch off point here is going to be a bit inside. And as they keep increasing VDS, the pinch off point goes further and further towards the source. So the channel becomes like a مثلث, ولكن no, the head of the triangle goes closer and closer towards the source. So this is really important. So why this is really important? Because basically what happens is that the voltage VDS, this voltage, has changed this, the length of the channel. See here? This is not the length. The length is L. So now L becomes L minus delta L, and delta L is this distance. Okay, that's what it is. So now the length is like this. So as I increase VDS, the length of the channel also decreases. Okay? Very, very important. We'll see why in a second. But before that, let's go back a little bit there and go to, oops, here. Which one? Oh, not this one. Okay. It's not shown in here, but let me try to see. Okay, 1 second. Okay. All right, here. Yeah, very good. So before I miss this, so I want to show you something really important here. I have to use the green. So remember here, so this is the transistor, the NMOS transistor. This. You have a question? If you need to talk, please, slowly and quietly, please. So, okay, so remember that the channel, when VDS was very small, was the whole length between the source and the drain. Was the whole length. That's what we said at the beginning. But now, when we developed the equations, the length of the channel went to the equation. So, but again, we'll come to that fact, but we said also that around N plus and under the channel, we have what we call the depletion region. So this region, which is this region here, around the diode and under the channel, is the depletion region. We don't have any charge in the depletion region. That means here in this area, when the pinch off push the channel there, that area becomes what? Depletion region. That means there will be no moving charge in that region. Only the charge will be in the channel. Otherwise, it's empty of charges. So that fact and this fact, we keep it in mind. So now, what we can say about this, in conclusion, we say that VDS actually changed L. It has modulated L, means it controlled L. So we say that we are in a situation where the channel length L is modulated or controlled by a voltage. And then we call this the channel length modulation effect. So the channel is being controlled by the voltage. This is a very important thing. Why? Because if you take it in account, so here, VDS, so let's recap. VDS controlled what? L. And became what? L minus delta L. Yes or no? I'll shrink it. This is what we call the channel length modulation. But then L, if you look at the equation for the saturation, we are talking about saturation so far, we know the conditions. L is also in the equation of the current, yes or no? Yes. That means, now L controls what? The current. ID, yes or no? So therefore, VDS controls what? ID. See? Now VDS controls ID. That means there is a resistance, yes or no? Makes sense? So if there is this, so there is a resistance now. We proved that there is a resistance between the drain and the source because VDS control the channel. And because the channel length also controls the current, so automatically they do. So in this case, I can put a resistance. I will call it R0 or R0. Okay. And then I will say, now ID is not going to be this simple equation that we studied before, but it will be rather I will have to add a parameter that will show me the dependence between VDS and ID. And how I do that? I keep this constant and multiply it by 1 plus lambda VDS, meaning that now the total current will be the current that I had before, which is equal to this, which is this. So this is this current. I will choose a different color now, plus a certain percentage of the current that comes this way. And how much that current is a certain percentage of this, meaning it is that plus this, which is this, this, and that's it. Okay, so they share the same factor, so it's this current plus a certain percentage of this current, represented by the parameter lambda, which is a certain constant, VDS. So here it says that now my ID not only is equal to the previous value, but that one plus a certain percentage of this times VDS. And lambda is actually the percentage of that current, okay, that we had before, VDS. That's it. So now this equation, show me, it's actually more realistic, and this is more experimental. We can see that. This happens only when we are really too far from the overdrive. So when we are at the overdrive exactly, we can say that we have this current, that's fine. But when we are too far from the overdrive, we have to add this parameter. And we will see that graphically in a second, okay? So this now is the new model of the NMOS transistor in saturation, okay? Any question? Good. Excellent. So next is the enjoyment of math. So remember that now we need to know lambda. What's lambda? How much is lambda? We need to know that. And we need to know R naught. How much is R naught? صح ولا لا? We need to know that. صح ولا لا? Good. So to know R naught, the resistance is nothing. The resistance is voltage divided by current. صح ولا لا? Or the derivative of the current by the voltage. صح ولا لا? Or I can write it as the derivative of the current versus the voltage inverted. صح ولا لا? This is correct or no? I can do that. It means a little change in VDS will cause a little change in ID, and then inverse this ratio, I will get the resistance R naught, which I put in the model. Correct? Where at a constant VGS means I have to keep VGS constant. If I do change it, then I'm in different graphs. Remember the example last time? We are in different graphs. We have to be on the same graph. Okay, good. Very good, excellent. So let's derive. So we have the equation that we started before, which is this equation. We derive this with respect to VDS, boom, 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 and we get basically this. So this is constant, gets out, and the derivative of this is nothing but lambda. So this is what? The derivative of this. So we have to make 1 over this. So to find R naught. You got it? Any question? واضحة ولا لا? Clear? Clear ولا لا? It seems I'm speaking in the cave. The echo is coming back. Do you understand? Any question? Are you following? Can I ask you? No, exam's over, huh? All right, good. Anyways, let's keep going. So this is now R naught. Very good, excellent. Now, let's write this. If we write this, remember here, look at this. This quantity, between red brackets, what is it? It is the current ID before we took account the channel modulation, yes or no? Because I'm using here L, the channel length. So here in the equation that we presented for ID, the new one, this one, for example, we kept L actually constant, and we said that instead of changing L and blah blah, I put L constant, but I put a parameter related to VDS directly through lambda. That's why. That's why lambda now, L is now kept constant here. Okay? But in fact it's changed. And anyways, so this is nothing but ID in saturation, yes or no? Correct? Fatma? This is ID, yes or no?
Yes.
Before we talk about channel modulation. صح ولا لا? Good. So this is ID, and you see 1 over, this is power minus 1. So if I put this under, so I have ID here, which is, see this, that's ID, okay? Now, we have on top, we have 1, yes or no? And we have lambda, is there. Very good. So resistance is equal to 1 over lambda I. Here I have a current. That means 1 over lambda is what? Is a voltage. صح ولا لا؟ لأنه it will be voltage over lambda, over current. صح ولا لا? So 1 over lambda, I will call it VA, a voltage. And that voltage, we call it early voltage. Because it was discovered by Mr. Early. And Mr. Early likes to have his name for the rest of the world. So now he died, but still we speak about him. Interesting. Yeah? Like Ibn Sina, we still speak about him. That's what scientists do. Alright, they leave something behind. And that's what they left. Knowledge. So VA now over ID is equal to R naught. Now, VA actually is a constant that is dependent on the fabrication process. So it's a constant. It will be given to you when you buy the transistor. It will give you VA. It's called early voltage. So you get early voltage, very good. You put your transistor, you get ID, divide VA over ID, and you get R naught. Very as simple as that. We make it more interesting in the next slide. In the next slide, this is what the real MOS is doing. So before we said what? We said we have the saturation current is actually constant. Comes here and gets constant. Yes or no? Yes. Excellent. But now, actually, the real MOSFET is actually there's a slope, especially when you are VDS far from the overdrive. Where's the overdrive? Is actually this, the intersection between the blue lines and this dotted line. Okay? So that's the overdrive. Here, 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 and etc. So now there is a slope. Now, how much is the slope? The slope actually, from the model, is actually, has the slope, or these lines have the slope of 1 over R naught. Okay, great. So how much is the slope? So Mr. Early actually, when he discovered this, is not out of the blue. He's actually, he took a ruler and put a line over all these lines here, like this. And he found all these lines intersect only one single dot. This dot. And he called it his voltage. He said, I found it here, you can't have voltage there. It's constant, it doesn't depend on VG, VGS or anything like that, because VGS has changed there, VDS changed there, ID also is changing, so it's independent of the operation of the MOSFET. So it must be something constant. Excellent. It's the same slope, huh? Not the same slope, it's the same intersection point. But slopes are different. Now, how to calculate the slope is very easy. It's this. Okay, for example, the slope here is actually this distance divided by this distance. Yes or no?
Yes.
Very good. Now, this distance, he already named it, is actually VA. The coordinate is minus VA, but the distance is VA. And now, we know that, huh? So now, how much is this? This, he said, is nothing but this value almost. They're very close to each other here. This point here, let me delete here. I don't have a magnifier, but you can understand my point. So he said this point, oops, I hate this, smart, so-called smart. So he said that this point here is almost same as this point here. And this point here is nothing but ID actually. So he chose this to be the same, and they call it ID before the modulation, which is what? Which is half Kn V over drive square. Yes or no? That's what we know before. Yes or no? So this divided by this, he will get what? The slope. Very good. So ID he calculated. So R naught. Sorry. The slope. What's the slope? Because the slope here is actually current divided by voltage. So it will be 1 over. Let's calculate the slope. Let's say slope. I'm calculating the slope, not the resistance. Huh? Slope is actually this, which is ID, divided by what? This, which is VA. But remember here, the slope is actually here, is actually opposite to resistance. So 1 over R naught. So R naught then is going to be equal to what? VA over ID. Yes or no? Which is exactly what we found here, is VA over ID. That's R naught. Correct? So, what I mean by this is that this is the graphical way to find R naught. Yes or no? This is the graphical way to know R naught. So if I need to know R naught, I don't have the data sheet, because if I have data sheet, it will give me VA, okay, and then I divide it by ID, I get R naught, that's it. So this is the way how to find what? R naught. Of course, this slope is different from this, different. Why? Because this one has different ID, this one has different ID, because this has different ID. Why? Because this guy has a different overdrive, this one has different overdrive, this one has different overdrive, etc. Do you understand? Yes. Alas? Step by step, but sure. We know what we're doing. What else? Yeah, before we go further, let's go back. Here, remember also the relationship between lambda and VA. They are opposite to each other, inverse. So VA is over 1 over lambda, or lambda is 1 over VA. And then I can take that and put it in the equation of ID. Or R naught, it's up to you. Do you understand? Good? Clear? Simple. Little bit complicated. Not big deal. Khalas? Okay? So that's the way, the graphical way of finding R naught. Could be potentially a question in the exam. So those who did not come today and felt very tired, they are not in a good shape. So they need to know that. Share with them. Okay, good, because I didn't put that for a reason, okay? So take note and be clear. If you have any question, right now, okay? Clear or not? Good, so let's move on. So basically now we explained the lambda parameter that is in the new equation when VDS is way bigger than the overdrive. We explained it, we find how to find lambda. Lambda is equal 1 over VA. VA is from the data sheet of the transistor, it's constant. Like Kn, Kn prime, etc. Alas, like mu n, Cox, etc. Alright, that's number 1. Number 2, we know the resistance now. We have now resistance. R naught. R naught is equal to what? VA over ID. Very good. Now if you give me VA, give you R naught. صح ولا لا? And it depends on the current. The more ID, the less is going to be what? The R naught. صح ولا لا? Very good. Very good. Now we go to the PMOS. As we said, we discussed it before, but here is just a repetition here. This is the symbol of PMOS. So the arrow of the body is going actually outward here. And the current in the PMOS goes from the source to the drain. Okay? In NMOS, it goes from the drain to the source. Remember that? And that's it. So this symbol, and this symbol, they are all the same. Of course, this symbol is the same as this one. Where is the fourth? The fourth is actually, the body is actually connected to the source, like we explained in the NMOS transistor. Okay? The body is always connected to the source. And we are not saying why. Just take it like this. Now, in terms of the equations, so to how to find really these equations, do I need to memorize this? No, I don't need. So the only thing is very simple, because PMOS is the mirror of the NMOS. In the mirror, the right becomes left, left becomes right, yes? Same thing here. So instead, so if I have the equations for the NMOS, I have to change every N by P. Very good, that's number 1. Also, the direction of the voltages and currents will be also opposite. صح ولا لا? Because electrons move against holes, yes or no? So instead of saying VGS, we will say VSD. See, VSD. Instead of saying VDS, we say VSD. And also, instead of VGS, yeah, we said VGS, huh? We said, VGS instead of VGS, because in NMOS, VGS has to be above VT. Now we have to say VSG. Okay, VSG has to be above, or VSG? What's that? No, above VT. Above VT. But VT here is negative, so we have to take the magnitude. Okay?
The magnitude is above black and I have.
Yeah, that's why you need to have to take absolute value. Yeah. So you have to take, here we are talking about absolute value, we are talking about this table. Okay? In any case, most of the time we will deal with NMOS just to make our life easier. You have suffered enough. صح ولا لا? So we'll use most of the time NMOS. But PMOS also will be on the table. Prepare for PMOS too. Okay? So, but exercises will mainly use the NOs. Okay, good. Let's keep going. An example. Now we are going to use a DC. We have here an example, so just here to add something here into the table. When we ignore the effect of the channel length modulation, means the control of the channel length by VDS, when we neglect it, means we do not account for it. We just say, I don't care much. So in that case, lambda has to go to 0. And the two equations become the same. When lambda goes to 0, R naught goes to where? Let's repeat. R naught, we said, is equal to what? VA over
ID.
I. And then VA is equal to what? 1 over lambda. ID. So when lambda goes to 0, R naught goes to where? So it means I can throw it away. There's no resistance. You understand? Understand? So when we say we ignore the channel length modulation, we mean two things. We can say that the resistance R naught is too high and can throw it away. And, or the same thing, lambda is equal to 0. I don't have to use lambda in my equation. You understand? Very important. Very possible to be in the exams. I repeat. So, when I say I don't, you see, when I say neglect the effect of the channel modulation, it means lambda equal to 0. That means I don't consider it. It is existing, but I don't count it. Khalas. It's an error, mistake, I love it. That's fine. I don't care. Khalas? But when we say lambda is equal to 0, it means also that R naught is equal to infinity. Too high. That means in my model I can throw it away. Because high resistance is an open circuit. Yes, correct? Yes or no? Following me?
Yes.
Tired after the exam. I can see. Okay, good. So we have here, so that's it. So let's study this, very, very quickly. I'm not going to study it. Who brought the textbook? If you brought the textbook today, I cannot believe it. After exam and blah, blah, you come and tell me, bring the textbook. Give me a break. There's no textbook after exam. See you next break. Huh? No, you need the textbook. Go to this page. When you go home, try to see the example here. I'm not going to solve this, but I'll give you the way how to solve it. Take notes. So this is a design question in which I have a given current ID. So ID, I set it. I want it. A customer come to me, say, I need a transistor, and they need the current on this transistor to be equal to this. 0.4 milliamp. It's a design question, huh? Because it's asking me to design. Okay, great. So, he gave me a transistor, so it means he gave me the data sheet of this. But he said also, listen, ignore the channel length modulation. Lambda is equal to 0. I tell him, thank you. And that's it. He just gave me, I didn't give me this voltage, this voltage. He tell me, what is the resistance here and here? That's the question. But he said that the output here, VD, is given. I give it to you. I need that. I need a certain current here, and a certain voltage here, and VD is given 0.5 volts. And he asked me those questions. And he gave me some numbers. Now, how to find these resistors? Anyone knows? So, we know this. We know this. That's it. What's that? Who knows? Raise your hand. We are not in souk. You? Go ahead. But VD over? Wallahi. Who agrees with this? Who agrees with this? Who has another answer? What's that? One only speaks. Yeah, go ahead. Yeah, speak. Go ahead. Yeah, continue. She said you answer. You. Go ahead.
VDD minus VD over
very excellent. So here we know what's going on. Very easy. So RD, straightforward, is VDD minus VD, because we know this. Bye bye RD. Bye bye. Use your calculator, enjoy.
ID.
Now RS.
ID.
Oh, over ID. Sorry. Over ID, yeah. Because we know ID. That's what we are looking for, actually. Getting old. I'm tired of the exams marking. Alright, good. So, this is RD. Now, RS. Who can answer the question for RS? How can find RS?
It will be 0 minus minus.
Just a second. She has. Okay, tell me.
ID will be minus minus.
No, I'm looking for RS, huh?
Yeah, because
صح, go ahead.
RS is 2.5 على ID.
دقيق. RS is how much?
2.5 على ID.
2.5 على ID. والله. Who agrees with this?
لازم نحسب الكرنت.
Just a second. Fatma?
لا, I don't agree with that. But I said we must find the current.
The current here, one more question. The current here is different from the current here or is same?
Same.
Why?
Because we ignore هذا.
Lambda?
Lambda is 0.
No, that's not the reason. Why this current is the same here? Who thinks that's different? It's the same. خلاص. Why? Because it's KCL. Kirchhoff current. The current comes in is the same as current comes out. صح ولا لا? Make sense? The current comes in is the same as comes out. Simple. لا لندى ولم يحزنون. صح ولا لا? Very good. Excellent. Now, back to her answer. Is her answer correct or not? And if not, why? So she said, divide this by this and then, or this by this and then that's it, RS.
No, we must.
So, wait. Who has an idea? Raise your hand. Yes, Fatma?
We must find V voltage before the resistor عشان.
What's that before resistor? What's called that? You mean here?
here.
What's this?
VS.
This is, oh yeah, source. Yeah, that's source.
Here source VS.
You wind up voltage, VS. Don't be shy. Yeah. VS, how much is VS? Do you know VS? Do we know VS? We don't know. Simple, yeah, we don't know. Is it written somewhere? مو مكتوب صح ولا لا؟ صح. So how to find RS?
VS minus.
VS minus?
VS.
Yeah, that's divided by?
I.
Very good. خلاص, excellent. So, let's see. RS is equal to VS minus VSS divided by what? I. We know this. So, do we know this?
Yes.
We know VS? We know VSS?
Yes.
Can we know RS? So to know RS, we need to know?
VS.
Excellent. See? Did you find your mistake?
Yes.
Never do that. KCL, KPL. So,
No, because I saw the
no.
ground.
Always to find, you have to look at the difference of voltage.
No,
Don't-
because I saw the ground there.
Where the ground? No, the ground. Where is the ground connected here? Good question.
Gate.
To the gate. تخربطت المواضيع. الجيت ولا source والsource ولا gate. صح؟ هذه yes, connected to the gate. Yeah. It's okay to make mistake. If you didn't do the mistake, you will not know this. That's nice. Now you know, huh? صح ولا لا؟ source والgate. صح ولا لا? We keep going? خلاص? We keep going. Please, if you need to talk, not loudly, please. We are going here. Okay, great. So, now to know RS, we need to know VS. صح ولا لا? How to know VS? See, we are going step by step. Huh?
From source.
Huh?
From source.
From the source. Hey, buddy. So, that's the voltage. That's the voltage here. How much? So I'll go now and tell you how to do it. But this is the step. We go step by step. صح ولا لا? This is how you should think when you solve these kind of problems. You understand? Very good. So we need VS. صح. Very good. So what we know? We know very importantly that, first and foremost, that this transistor is working, because that's the first question we know, is working in saturation. Why? Because he told me it's lambda and neglect lambda. Lambda exists only in the saturation. Number one. MOSFET is in saturation. You can write that down. Okay, good. And number two, I know the current in saturation. صح ولا لا? Is equal to what? ID is equal to half K and V over drive square. Yes or no? ID is given. Do we know ID? Yes, it's given. Yes or no? Kn we know. Kn is equal to what?
W over L.
Yeah, W over L.
COX.
COX. في mu n. الله دمرك الإجزاء. خلاص memory is gone. Very good. Yeah. So mu n COX here times W over L and خلاص. So Kn is given.
نطلع VOX عقب نسوي
وين
VOX equal VT.
وين VOX? There's no VOX.
VOV I mean.
Very good. Very nice. Excellent. Now the remaining is VOV. Yeah. Okay. Let's go for VOV. So VOV is equal to what? Let's see. V overdrive is equal to what? Can somebody tell me? V overdrive is how much?
Square root.
Wait. What's the overdrive? Not from this equation. What is the overdrive voltage?
Equal VDC.
V?
VDS.
VDS. Very good. You need to take a very long break. Who else? Okay, who else? The overdrive is VGS minus VT. We explained that many times. صح ولا لا?
هي بس هي equal V.
Wait.
Minimum. VDS في saturation.
We did not say we are in the minimum. Did we say anything like that?
No.
We know only we are in saturation. صح ولا لا? So don't invent things. Don't say that I didn't say. Let's say this is a problem and then you say, no, you said this. I didn't say that. صح ولا لا? I didn't say that, did I? Okay, good. So V overdrive is equal to VGS minus VT. Good. So that's what I need to know. صح. VGS, how much is VGS? VGS is equal to VG minus VS. VG, what is the one? She left. She found it, VG. VG is equal to?
0.
So 0 minus, so I write it in different color. 0 minus VS. صح ولا لا? That's my VGS. Make sense?
Yes.
Now things are coming. You see? Excellent. Very good. So V overdrive is equal to 0 minus VS minus VT. So very good. So the overdrive is equal to what? Minus VS minus VT. Make sense? Yes? Very good. Excellent. Now, we have lots of stuff here. Okay. So the overdrive is related to VS and VS is related to RS. So if I take VS from here and put it here, then put it here, I will have an equation of second order. صح ولا لا؟ لأنه VS is equal to what? Here. VS is equal to what? Here, VS is equal, from this equation, is equal to
RS في ID plus VS.
RS ID
plus VS.
plus VSS. So RS ID plus VSS. So now I come here and put it there. صح ولا لا? So I will try to say that the overdrive is equal to, is minus VS, yani minus this one, yes or no?
Yes.
So it will be minus RS ID
minus VSS
minus VSS
minus VT.
minus VT. What do I don't know? I know this, I know this, I know this idea. I don't know only this, huh? So if I put this equation where here I will have everything except RS and V overdrive get squared. So here we'll have what? RS squared. So it will be second order equation and it will have two solutions. RS1, RS2. Yes or no? Then when we solve for RS, so we have to choose. One of them will be nonsense. Why? Well, let's see. Nonsense in what sense? It has, I have to have the condition, one of the conditions here is that the saturation here, the transistor is in saturation, meaning what? That VDS, which is this voltage, VD minus VS, has to be bigger than the overdrive. Yes or no? Because we are in saturation. Yes. So one of them will violate this condition, that's for sure. Okay? Or will violate, for example, I don't know. Because RS is where? It is actually in V overdrive. Maybe will violate the channel itself. Maybe the channel will not exist. Do you understand? Things like that. So, in other words, One of them I have to try where in the overdrive, for example, or compare, check that my voltage here, the condition for saturation is satisfied, meaning VDS. I have to make sure that RS1 or RS2 always satisfy that VDS is above V overdrive. صح ولا لا? In V overdrive I have RS. VDS I have it too. In VS also here I have RS. So if you take this equation, you will be able to find the right RS that will be taken as a solution. And the problem is over. Got it? Nice. Sweet. Easy to some extent. Not after exam. After exam we are dead. صح ولا لا? Good. Anyways, have a look at the solution, and if you have problems, ask me. Now we move quickly, because we need to finish today's class, to the small signal operation. Now we know the model of the MOSFET. Next is to use it to amplify. So I have to put a MOSFET in a circuit. It has to be what? The first thing, it has to be in saturation. This is the condition number one. And how do I make? Is through the control of VGS. So VGS, and of course, through this resistor, which will set this voltage, I can make, through this resistor, VDS above the overdrive of this transistor. Once I'm satisfied, I know how to do it. Later on, we can study that in the biasing chapter. Then once I'm done with that, I just come and put an AC signal on top of my gate. So now, the total instantaneous voltage here across the gate, or between the gate and source, is equal to a DC voltage plus an AC voltage. Remember this? Small letter, capital, subscript. Remember? Very good. Very good. Very good. The only condition here is that VGS is actually small. We'll see later on how small. The value of means small. But for now, it is small. خلاص? That's it. So basically, this is a typical configuration of an amplifier. Simple, but they are more complicated. Okay? So, okay, great. So, I need to know now my amplifier. The first characteristic is that what we said, that the transistor will take the voltage VGS and send me a current. But the voltage VGS now, it has both a DC value and an AC value. VGS minus VT squared. This is what? This is the equation of ID in saturation, because this transistor is working in saturation, yes or no? And of course, we did ignore lambda. We said lambda is equal to 0 to make the calculation simple. Okay? So this is the saturation current. Very good. And then we replace this. We just manipulated things. We put minus VT beside the VGS, and we squared everything, and we get these terms. Okay? There's no square there. When we develop this, you get this. Very simple. Which is the whole thing is this, basically, is this square. And then what we do, that's it. We get that equation, and then I don't want to waste your time, and I put it in a single long equation, which is this one, multiplied by Kn and half, blah, blah, we get this. And then I try to observe, what I observe, that this term here, this part, you have a constant times the DC values here. And apparently this one, I know this. This is the DC current, or what we call the DC bias. I'll explain later what we mean by bias. But for now, is the DC current ID. So remember, this is the instantaneous. Okay? And this is the DC. Now, the AC then will be the whole thing here. صح ولا لا? So if this is DC, then this is the ID. Because this is at the output, yes or no? This is the drain current. So it has a DC component plus an AC component. The AC component has two terms. This term, which is a constant, times the AC, and plus constant times this AC squared. So this, because the order is 1, we can say this is a linear relationship of this AC term with VGS. So it has a linear gain term. And this one is non-linear. Why? Because it has power 2. Here is basically the condition to minimize this value to this value. I'll tell you that in a second. We said also VGS is so small that it's small enough that if we square it or quadruple it or whatever power is, that value becomes even smaller and smaller. It's like 0.1 power 2. It will be 0.01. Yes or no? It's even smaller. Huh? So small value of power, it will be even smaller. So that's why we say, I don't need you. I can live without you. Fine. It's a small thing that I will, I can throw away. It's like throwing 50 fits. Or throwing a dirham when I go to Carrefour. Who cares? I put it in somebody will take the 1 dirham. Who cares? But here, 1 million dirham, I will not throw it away. So something like that. So this is not only non-linear, but it's also small. So I can throw it away. Now, when we say throw it away, actually we are doing this. We are comparing this to this, or this to this. Which leads us that VGS, how small it is, it needs to be smaller than 2V over drive. This is how small VGS need to be. You can follow that. It's not really big, just simple math. Okay? So this gives me the magnitude, the order of magnitude of VGS to be considered as small. Anyways, now we have this. Let's keep going because we need to go goodbye soon. All right. Oh, thank you, Microsoft. So this term now is actually that's the AC signal. What's the AC signal? Of the current. Then we are talking about the current. We said this is the DC, and this is the AC, and this is the instantaneous. Very good. So thank you very much. So I have a relationship between the input AC signal with the output AC signal. Here is a voltage, here is the current. When I have a voltage and current, I have a resistor or something like that. Here in this time, we are doing something really interesting. Let's divide the output, VGS, or, well, the output, the output is this one. Let's write this one. So remember, this is the output and this is the input. This what caused this, yes or no?
Yes.
So, this is what? The input. So let's then take ID, the output, divided by the input. Here is the current and this is the voltage. It's actually 1 over ohm. Yes or no? It's the reverse of? Resistor. Reverse of the resistor is a conductor. Conductance, actually, if you remember. Yes or no? And that's why we call it transconductance. Trans, why? Because coming from the input, translated to the output. It transfer. Huh? It transfers the signal from the input to the output, and it's conductance. Because it's a unit of conductance, 1 over ohm. Very good. When I do that, this is ID divided by VGS. I get this constant, which is really interesting, and we call it transconductance parameter, GM. And this is how the value is dependent only on VGS. So the conductivity here, or the transconductance actually, is actually proportional to VGS. The more VGS I have, the higher my transconductance. We'll see the implications. Not today, because it's too much. Almost to close today's class, to see another perspective. And that is, basically, if I draw, so basically, a transfer curve, if you will, but it's not really transfer characteristic, is actually, it's almost like, why? Because VGS is actually the input, yes or no? This is the input. What's the output? Is this one. So if my output is a current, so if I take my output and see how it does change with my input, I will find this curve. We already discussed it before, but what I want to tell you here is that, first of all, this curve is made only where? In saturation. Because that's where my amplifier is working. So I know the equation for that. For ID, ignoring lambda, is going to be half Kn times V over drive square, and V over drive is nothing but VGS minus VT. Yes or no? Yes. So that's why you have this like this. And it has to start from VT. Do you understand? Because below VT, there's no channel at all. It disappears. Okay, so what it means here, let me explain this. So my transistor, this is the transfer curve of my transistor. And this is the total instantaneous voltage with my circuit. So I can put my transistor to work on this point. Why? Because I put the DC bias VGS with the battery that you saw just now at this point. So at this point, my current, my DC current, need to be in this level. So, as soon as I do that, I put the battery, then I put the AC signal on top of the battery. That means I create a variation of the total voltage across the gate. Yes or no? So my gate now, it has a DC, but it does vary on top of the DC. Yes or no? So that means my output current will also vary. What? Will vary accordingly. Yes or no? Meaning, let me give you an example here. What's that? What's that? لا بعيدة yeah, just a second. So my transistor is working on this point. We call it the operating point or the bias point. We'll come to that later. Huh? This is where I put my transistor to work. Now, when I put, so this is through what? Through this battery, VGS. This battery, remember this? Where is the circuit? You have to have that circuit always in mind, okay? Through this. So this, that sets my point, VGS. So this battery puts this transistor to work at a certain point. And that point is this one. Okay, thank you. Oh, okay. Now, that point is this point. Khalas? When I put on top of it this AC signal, small v, small VGS, that means I create a little variation on top of the DC. You understand? So now the total value is going up and down around this DC. So for example, when my AC bring my DC a little bit smaller, that means in here value, so my ID will be here, yes or no? When it goes up here, for example, next, so my new current will come here. So it will do like this. You understand? It will follow. So this, for example, this time, okay? This is the time axis. That means if it change here, change there. It's like what? It's like shining the mirror light like this, reflection. So my input change from here to here. My output current will also change from here to here. It's like amplification. Do you understand? That's what it is. Because through the curve of this transistor, that's how my response. So this is my what? Output. Because I told you this is my output since the beginning. And this is my input. My input changed like this. My output will change like this. Around what? Around this point that we call the operating point. Excellent. That's exactly what's happening. So there's a kind of amplification there. Oh, excellent. How much is that? Is through GM. GM basically tells me how my output changed versus input. It means if my input change, how much is my output? Yes or no? It's actually the slope. This is the slope of this curve. Yes or no? Where? At Q. So if I draw a slope on this point, I will find GM. Okay? All right, great. So let's calculate this. So this is ID. Yes or no? Let's make a derivation. Let's do it, huh? Let's do it, ladies, huh? So if I derive this, this is constant, yes or no? So I have to derive this. صح ولا لا? Here, I know how to derive this. This is equal to what? The derivation of this is going to be equal to derivation of VGS here is going to be 1. صح ولا لا? Deriving here, you have to go math. I cannot teach you math. Okay, 2 لأن الأوردر اللي هنا is 2. صح ولا لا؟ هنا 2. فهمنا ولا لا؟ So 2 has to go down. The derivation inside is equal to 1, okay, with respect to VGS. VGS هو المتغير, okay? Times this power, this minus 1, times VGS minus VT. Very good. So if I take this and so this is this, the whole thing, and then multiply by this, you get this multiplied by this. You take this, multiply by this, it will become half with 2 gone, Kn VGS minus VT. And that's exactly the value found before. So that one is the graphical way, this one analytical way. But they are the same. Enjoy in the break, okay? Absolutely, this is a different way, but that one is graphical and this one is analytical, using equations. Because we are using math. Math is the same language. We are not lying to each other. Have a look at it. If you have a question, let me know. All right. Now we just finished with this term. That we need to do that actually. So now we said that, before we said that, if we change the voltage here with an AC signal, we will have a change of current here. Now what about the voltage itself? Here, the voltage also will change. Now we need to know the gain of the output voltage versus the input voltage. For that, all what we need to do is to express our voltage VDS. How much is VDS? It's nothing but this voltage minus the drop of voltage here, which is RDID. Yes or no? VDD minus RDID. And then ID, it's equal to IDDC plus the ID AC. So we just express this by its values, which are these two. Because this is the total current. Very good. And then what we do, we just put the DC component, which is this times this plus this, together. And the AC component, which is minus RDID, alone. Very good. Excellent. So this is what? This is the DC voltage of VDS. So if there's no AC, VDS, DC is equal to VDD minus RDID. That's it. This is the DC value of VDS. That's it. And this is what? Then automatically this is going to be the AC value, small v, small ds, of VDS, because this is the total instantaneous. Remember? It's DC plus AC. So now the AC voltage, the output is nothing but minus RD times the AC current. Excellent. That's our AC voltage. That's it. I have the AC voltage and I know ID. ID is actually equal to GM VGS, the equation we just discussed. This is the input and this is the output. Oh, excellent. VDS is equal to this. This is the input. So in order to calculate the gain, which is the output voltage, small AC VDS, divided by the AC VGS, this is my output and this is my input, that's the voltage gain. So this one divided by this, it can give me this. So the gain is negative. Okay, there's a minus there, it's possible. And it has also magnitude. Excellent. What are the consequences for this? Is this. And that's it for today. So, if I have here VGS, this is the total voltage. It has a DC voltage, and on top of that I have the AC signal, okay? That's the peak-to-peak voltage, okay? If I have this at the input of that circuit, at the output of my circuit, which is VDS, that's my circuit, depends on my circuit, on that circuit we are studying, my circuit will have also a DC voltage, VDS, and will have also an AC voltage, and I know the gain. This range divided by this range is equal to GMRD. That's number one, because that's the gain I found. That's number one. Number two is that when the input, the AC input, is positive, the other one is negative. I mean, when it's up, the other one is down. When it is down, the other one is up, because the gain is actually negative, you see? So, it basically reverse the waveform of the AC signal of the input at the output. Or, in other words, they have a phase shift of pi, of 180. And that's it for today. I know you are broken. Good luck, breathe, revise, enjoy, and see you inshallah next after the break. Wait for the project. All right. Go ahead.
Project before hours.